In a selective type switchgear configuration, a tie circuit breaker serves to connect two or more switchgear units together, enhancing redundancy and ensuring backup power availability. Determining whether to utilize a 3-pole or 4-pole tie circuit breaker hinges on several crucial considerations. Firstly, the presence of line-to-neutral loads is a determining factor. If the electrical system incorporates any line-to-neutral loads, implementing a 4-pole circuit breaker becomes mandatory. This is because the 4-pole breaker provides a dedicated pathway for the neutral current to safely return to the source. Secondly, the type of grounding system that is employed is a critical element. In scenarios where a single-point grounding system is in place, employing a 4-pole circuit breaker becomes essential. This ensures the consistent integrity of the grounding path, maintaining safety and proper operation. Thirdly, the presence of harmonics and neutral currents must be addressed. Nonlinear loads are notorious for generating harmonics and injecting substantial neutral currents into the electrical system. These elevated neutral currents can potentially overload the neutral conductors, potentially leading to equipment damage or system malfunctions. Opting for a 4-pole circuit breaker offers a low impedance route for these neutral currents to flow, thus mitigating the risk of overloading and safeguarding equipment. In the specified case, the nominal voltage is 480V/277 volts, 3-phase. The grounding system in place is not a single-point grounding system. The load type is characterized by nonlinear loads. Given that there are no line-to-neutral loads directly connected within the system, a 3-pole tie circuit breaker could theoretically suffice in providing redundancy and backup power capabilities. However, it is crucial to recognize the potential for elevated levels of neutral current and harmonics stemming from the presence of nonlinear loads. To effectively address this concern, selecting a 4-pole circuit breaker emerges as the preferred solution. A 4-pole breaker offers a low impedance pathway for neutral current to circulate, substantially diminishing the adverse impacts of harmonics on the overall electrical system. Considering these aspects, and accounting for the distinct demands of the specific application, it is generally recommended to employ a 4-pole tie circuit breaker. This choice will not only assure the integrity of the grounding path, but also furnish a low impedance route for neutral current flow, thereby minimizing the potential impacts of harmonics and bolstering the reliability of the system. When dealing with harmonics, it's crucial to understand their nature and potential effects. Harmonics are currents or voltages with frequencies that are integer multiples of the fundamental frequency of the power system, typically 60 Hz in North America. Nonlinear loads, such as variable frequency drives, electronic ballasts, and uninterruptible power supplies, draw current in a non-sinusoidal manner, injecting harmonic currents into the system. These harmonic currents can cause a variety of problems, including overheating of transformers and conductors, misoperation of protective devices, and increased losses in the system. The neutral conductor is particularly susceptible to overheating when significant harmonic currents are present. In a balanced 3-phase system, the neutral current should ideally be 0. However, harmonic currents, especially odd-driven harmonics like the 3rd, 9th, and 15th, add arithmetically in the neutral conductor instead of cancelling out. This can result in a neutral current that is significantly higher than the phase currents, potentially exceeding the conductor's ampacity and leading to overheating or even fire. A 4-pole circuit breaker helps to mitigate this issue by providing a dedicated and adequately sized neutral conductor path, ensuring that harmonic currents can flow safely without overloading the system. Furthermore, the grounding system plays a vital role in managing harmonic currents. A properly designed grounding system provides a low impedance path for fault currents and helps to stabilize the voltage during transient events. In a system with nonlinear loads, it is essential to ensure that the grounding system is capable of handling the increased harmonic currents. This may involve using larger grounding conductors, implementing dedicated grounding electrodes, and employing harmonic filters to reduce the amount of harmonic current injected into the system. Single-point grounding, while generally preferred for sensitive electronic equipment, may not always be the most practical solution for large industrial facilities with extensive nonlinear loads. In such cases, alternative grounding schemes such as multi-point grounding or impedance grounding may be more appropriate. The choice of grounding system should be based on a thorough analysis of the specific application, taking into account the type and amount of nonlinear loads, the sensitivity of the equipment, and the overall system configuration. When selecting a 4-pole circuit breaker, it is important to ensure that it is properly rated for the application. This includes considering the voltage, current, and interrupting rating of the breaker, as well as its ability to handle harmonic currents. The breaker should also be equipped with appropriate protection features such as overload and short circuit protection to prevent damage to the equipment and ensure the safety of personnel. In addition to the circuit breaker, it is also important to consider the other components in the system, such as transformers, conductors, and switchgear. These components should be properly sized and rated to handle the increased harmonic currents and voltages. It may also be necessary to implement harmonic filters to reduce the amount of harmonic current injected into the system. Harmonic filters are passive or active devices that are designed to attenuate specific harmonic frequencies. Passive filters typically consist of inductors and capacitors that are tuned to resonate at the harmonic frequency, providing a low impedance path for the harmonic current. Active filters use power electronic converters to inject harmonic currents that are equal in magnitude but opposite in phase to the harmonic currents produced by the nonlinear loads, effectively cancelling them out. The selection of harmonic filters should be based on a detailed harmonic analysis of the system. This analysis will identify the dominant harmonic frequencies and determine the appropriate size and type of filter required to achieve the desired level of harmonic mitigation. In addition to the technical considerations, it is also important to consider the economic aspects of selecting a 3-pole or 4-pole circuit breaker. A 4-pole breaker is typically more expensive than a 3-pole breaker, and the cost of implementing harmonic filters can also be significant. However, the cost of not addressing harmonic issues can be even higher, including equipment damage, increased energy losses, and reduced system reliability. Therefore, it is essential to perform a thorough cost-benefit analysis to determine the most appropriate solution for the specific application. In summary, the selection of a 3-pole or 4-pole tie-circuit breaker for a 480W/277V system with nonlinear loads depends on a variety of factors, including the presence of line-to-neutral loads, the type of grounding system, and the potential for harmonic currents. While a 3-pole breaker may be sufficient in some cases, a 4-pole breaker is generally recommended to ensure the integrity of the grounding path, provide a low impedance path for neutral current, and mitigate the impact of harmonics. It is also important to consider the other components in the system, such as transformers, conductors, and switchgear, and to implement harmonic filters if necessary. A thorough analysis of the technical and economic aspects of the application is essential to determine the most appropriate solution. It's also important to follow the National Electrical Code, or NEC, guidelines when implementing a 4-pole breaker or any electrical system. The NEC provides comprehensive requirements for the safe installation and operation of electrical equipment, including conductors, overcurrent protection devices, and grounding systems. Article 220 of the NEC covers the calculation of branch circuit, feeder, and service loads. This article provides specific requirements for calculating the neutral load in a 3-phase system, taking into account the presence of nonlinear loads. Article 250 of the NEC covers the grounding and bonding requirements for electrical systems. This article specifies the size and type of grounding conductors, as well as the methods for grounding equipment and systems. Article 300 of the NEC covers the general requirements for wiring methods and materials. This article specifies the types of conductors that are permitted for use in different applications, as well as the requirements for installing and supporting conductors. Article 310 of the NEC covers the ampacity of conductors. This article provides tables that specify a maximum current that a conductor can carry safely, taking into account the conductor's size, insulation type, and ambient temperature. Table 310.15b16, formerly Table 310.16, is commonly used for determining the ampacity of insulated conductors rated up to 600 volts. Article 408 of the NEC covers switchboards and panel boards. This article specifies the requirements for the construction, installation, and wiring of switchboards and panel boards. In addition to the NEC, other standards and guidelines may be applicable to the design and installation of electrical systems with nonlinear loads. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers IEE and the International Electrotechnical Commission IEC. IEE Standard 519 provides recommended practices and requirements for harmonic control in electrical power systems. This standard specifies limits for harmonic voltage and current distortion at the point of common coupling between the utility and the customer. IEC Standard 61000-3-2 specifies the limits for harmonic current emissions for equipment connected to low-voltage public power systems. It is also important to consult with a qualified electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes, standards, and regulations. A qualified engineer can perform a thorough analysis of the system, identify potential harmonic issues, and recommend appropriate solutions. Furthermore, regular maintenance and testing of the electrical system are essential to ensure its continued safe and reliable operation. This includes inspecting conductors, connections, and overcurrent protection devices, as well as performing harmonic measurements to monitor the level of harmonic distortion in the system. In conclusion, while the absence of line-to-neutral loads might suggest the adequacy of a 3-pole tie-circuit breaker in a 480Y/277V system, the presence of nonlinear loads necessitates a more comprehensive approach. The potential for harmonic currents and their detrimental effects on equipment and system reliability cannot be ignored. A 4-pole circuit breaker, coupled with a well-designed grounding system and potentially harmonic filters, offers a robust solution. Adhering to the NEC guidelines and consulting with qualified engineers are paramount to ensuring a safe, reliable, and code-compliant electrical system. This ensures not only the longevity of the equipment, but also the safety of personnel and the overall efficiency of the operation. Remember to consult the latest edition of the NEC and any applicable local codes or regulations when designing and installing electrical systems. The information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. The proper selection and application of electrical equipment require a thorough understanding of the system requirements and the applicable codes and standards. Proper grounding is extremely important. Grounding ensures a low impedance path for fault currents, allowing protective devices to quickly clear faults and minimize the risk of electrical shock. A properly designed grounding system also helps to stabilize voltage during transient events and reduce electrical noise. The grounding electrode system typically consists of one or more grounding electrodes such as ground rods, ground plates, or underground metallic water pipes that are connected to the grounding conductor. The grounding conductor is then connected to the equipment grounding conductors, which are connected to the non-current carrying metal parts of electrical equipment. The size of the grounding conductors and the grounding electrodes must be in accordance with the NEC. The NEC specifies the minimum size of the grounding conductor based on the size of the overcurrent protection device protecting the circuit. The NEC also specifies the minimum size and type of grounding electrodes that are permitted. Bonding is another essential aspect of electrical safety. Bonding ensures that all non-current carrying metal parts of electrical equipment are electrically connected together, creating a low impedance path for fault currents. This helps to prevent voltage differences between different parts of the equipment, which can pose a shock hazard. Bonding is typically achieved by using bonding jumpers to connect the metal parts of electrical equipment together. The size of the bonding jumpers must be in accordance with the NEC. The NEC specifies the minimum size of the bonding jumper based on the size of the circuit conductors. In addition to grounding and bonding, surge protection is also important for protecting electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching operations, and other transient events. Surge protected devices, or SPDs, are designed to divert surge current away from sensitive electrical equipment, preventing damage. SPD are typically installed at the service entrance and the branch panel boards. The selection of SPD should be based on the surge current capacity, the voltage protection level, and the type of equipment being protected. In summary, the selection of a 3-pole or 4-pole tie circuit breaker for a 480W/277V system with nonlinear load requires careful consideration of various factors, including the presence of line to neutral loads, the type of grounding system, the potential for harmonic currents, and the applicable codes and standards. A 4-pole breaker is generally recommended to ensure the integrity of the grounding path, provide a low impedance path for neutral current, and mitigate the impact of harmonics. Proper grounding, bonding, and surge protection are also essential for ensuring the safety and reliability of the electrical system. Remember to consult with a qualified electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes, standards, and regulations. The information provided here is for general guidance only and should not be considered a substitute for professional engineering advice.